Back Physics 30. This is the last part of the FI 1.3 video. People and other, so we look at weightlessness. People and other objects in a satellite circling the Earth are said to experience apparent weightlessness. Let's first look at a simpler case. For example, a falling elevator. In the figure on the right, an elevator is at rest with the bag hanging from a spring scale. The scale reading indicates the downward force exerted by the bag. This force exerted on the scale is equal and opposite to the force exerted by the scale upward on the bag. So if we recall, if I was to look at that bag there, we did this before, right? We have Fg pulling downward, and I can call it tension force pulling upwards, equal and opposite. So gravity pulling down, because it is not accelerating up or down. So Fg, of course, is equal to mg. And Ft, what we see that the reading on the scale, it's actually the tension force, but we often call that weight, which of course is equal and opposite to the force of gravity in this scenario. So call it weight, or I can call it just in quotations W. Okay, and in this case it's equal to mg. If we're not moving, or if we're moving at constant speed, right, the net force would be 0 as well. Okay, so the scale reading indicates the downward force. This force exerted on the scale is equal to and opposite to the bag, yes, and we can call it W for weight. Two forces act on the bag, the downward force of gravity and the upward force exerted by the scale equal to W. Because the bag is not accelerating, and if we apply this, we get this. So the total force, F net. So earlier we would have said, okay, so vertically, F net is equal to all the forces that are involved vertically. Vertically, I have Fg pulling downward and W pulling upwards. And if we were not accelerating, or let's say the elevator was moving with constant velocity, F net would be 0. So W and mg would be equal to. Okay, so, or if I was to subtract mg, I would get W is equal to the negative of mg, right? And of course, you usually put negative 9.8 in for g here. So if I take the negative of that, I would get a positive value. Okay, so that's what that works out to be. So for example, if I had a mass that was 1 kg, okay, if I had a 1 kg mass, oh, that's turned out messy. Of course, Fg is equal to mass times gravity, so 1 kg multiplied by negative 9.8, that would give me negative 9.8 is what this part would be. So if I just redo this over here, 0 is equal to W plus Fg, 0 is equal to W, and then plus, if Fg is negative 9.8, because it's a 1 kg mass, then to solve for W, it's just simply equal to 9.8 to the positive. So 9.8 newtons versus negative 9.8 newtons. And that, we can see that. So that scale reading is really telling us what Fg is, even though it's equal and opposite. So thus W is equal and opposite to mg, and since the scale indicates the force W exerted on the bag, it registers a force equal to the weight of the bag as we expect. Now, let the elevator have an upward acceleration. So that moment in time when the elevator is going from 0 to some velocity that you experience in that elevator. It's a very quick moment, but we could say that's the time period in which it is happening. So we would have the same thing here. We'd have 9.8, but this time we're not going to have F net equals 0. Okay, so overall, let's say I am accelerating, let's say I'm accelerating at 9.8. Okay, so say A is equal to, we're accelerating upwards at 9.8 meters per second. Okay, so in that case, F net, if I know my acceleration and if I know my mass, oops, 9.80. newtons upwards. So I would have 9.8 as my net force. And if I'm looking at what I had here previously, Fg is still a 1 kg mass. So it is experiencing negative 9.8 here. And if I'm looking for W, something interesting happens here. W works out to be 9.6. Now that's a very high force, a very large acceleration. But this would appear that I would heavier. So when moving up in an elevator, that sensation that you feel, that heaviness, is in fact what you would feel because you're accelerating upwards. So this would appear to be much heavier than it is. So it would appear that you're gaining weight. So we have chosen the positive direction up. Thus, if the acceleration of A is up, and the scale which measures that will read more than Fg would be if it was at rest or moving at constant velocity. We call W the apparent weight of the bag, which in this case would be greater than the actual weight of Fg. If the elevator accelerates downwards, A will be negative and the apparent weight will be less. Well, let's take a look at that scenario. Let's say A is negative 9.8. So let's say we're moving downwards. Say we're moving downwards. So again, F net equals MA. So my 1 kg mass experiencing falling. So if I look at my scenario here again, vertically, W plus Fg. So if I'm falling down, and Fg is this, add 9.8, add 9.8. So if you're falling at the rate at which gravity is acting, you would appear to be weightless. So that is apparent weightlessness. So it's less than Fg, and if it just happens to be the same rate at which gravity is acting, you would in fact be zero. So only the directions of acceleration and its magnitude would affect the scale reading. If the elevator is in free fall, if the cable breaks and the scale reads 0, just like I calculated right here. So you would have apparent weightlessness if you're following at the rate at which gravity is acting. So the person in the elevator at free fall, if the person in the elevator at free fall let go of the box would not fall to the floor. It would just simply float there, just like the person would be. So the box is falling, but in terms of the person inside the elevator, things appear to be weightless. But so the floor and the elevator pressure, the box would hover right in front of the person. This phenomenon is called apparent weightlessness to the person inside. Of course, if it was a glass elevator and someone on the outside was looking at this, they would see everything fall. But according to the person inside, that's the apparent weightlessness. So if you look at, quite often you see videos of astronauts training in an airplane. That airplane is actually falling at the rate of gravity, so everything inside appears to be weightless. So gravity is still acting on it, but because of the movement of that object, weightlessness, it looks like it's happening. So let's do an example, a further example with this, very similar to what we did on the previous page. 10 kg mass is hanging suspended by a spring, scale in an elevator. What will the spring read if it's rising at constant speed, falling at constant speed, first of all? First of all, let's figure out this. We know we're going to be using this, Fg equals mg. So it's a 10 kg. So negative 98 newtons is the weight, the actual weight of the object. If we look at this, F net, so vertically we have the apparent weight, the scale pulling up on the object, and Fg, the earth pulling on the object. Now, if I am constant speed, both of these, constant speed, in fact, what I can do here is I can say A and B, because guess what? We're going to get the same result. At constant speed, A is equal to 0. And if A is equal to 0, then F net is equal to 0. So we have 0. So plus negative 98. So solve for W. W equals 98 newtons. So that's for A and B, whether I'm falling or rising. If it's constant speed, A is equal to 0. I'm not accelerating or decelerating, so we get that. C, if I'm rising at 2 meters per second though, or sorry, that is my acceleration, so I'm changing by 2 meters per second every second. So F net is equal to my mass times positive 2, because we're going up, 20 newtons. So working this again, so vertically, this is what I have happening. Now over here, of course, I have my overall force that results is 20. I have my W, and I have negative 98. So if I'm moving up, you should feel heavier, right? What we saw from before, and in fact, that's what happens here. So even though we know we're 98 newtons, we apparently are 118 inside the elevator. That's what we experience. And of course, what if we're rising at -2? So rises really means, I guess, falling here, because we're rising negatively. That means going towards the Earth. So of course here F net equals MA. This time we're going downwards though, so it's negative 20 newtons. So very similar working out here. So negative 20, negative 98. Add 98 to isolate W. This time W appears to be 78 newtons. So we appear to be lighter when we're moving downward. Okay, so our actual weight is 98. Moving upwards, we appear to be heavier. Moving downwards, moving with gravity, we appear to be lighter. All right, you should be able to do the assignment now. Just remember number 5 is kind of that big one in which you solve for the 2 velocity equations. But I guess we have one more question here, one more side. So the weightlessness experienced by people in a satellite orbit close to Earth is the same as the apparent weightlessness in an elevator. It may seem strange at first to think of a satellite as freely falling, but a satellite is indeed falling toward the Earth, as was shown earlier. The force of gravity causes it to fall out of its natural straight line path, because remember, it gets launched out and it has to have such a speed so that it doesn't escape this orbit, it doesn't go below the orbit, it stays in the orbit because it's constantly being pulled inwards by the Earth. So it has to have a high enough speed to stay in that path. So it falls out of its straight line path, because otherwise, yes, it would want to go outwards. The acceleration of the satellite must be the acceleration due to gravity at that point, because that's the only force acting on it. Thus, although the force of gravity acts on objects within the satellite, the objects experience an apparent weightlessness because they and the satellite are accelerating together in free fall. So it's like this scenario. They're falling downwards towards where gravity is being exerted from. Completely different situation occurs if a spacecraft is out in space far from the Earth, the Moon, and other attracting bodies. The force of gravity due to the Earth and other celestial bodies is quite small, or even 0. If we're using very large distances. And of course there they would experience what we would call real weightlessness, because there's nothing pulling them down. All right, so there you have it, ladies and gentlemen. So you should be able to do the assignment now, and we'll see you again.